For this afternoon, we'll cover the remaining topics on our module in solutions. But before that, we're going to review what we have discussed last meeting. Okay, last meeting, we have started discussing on the factors affecting solubility. And we have the solid-solvent interaction in here. And as what everybody would recall, that if we're talking about the chain, a hydrocarbon chain, the longer the chain, the less soluble it is in water, because of the primary fact that polar solvents, polar solute gets dissolved in polar solvent. So like dissolves like. So if you have a polar solute, then your solvent has to be polar. If you have a non-polar solute, your solvent has to be non-polar as well. Then we also have discussed that as we increase the OH groups for our organic materials, the molecule increases solubility in water. So this is the case of the alcohol. Then concerning also the solubility, this table was presented to you, wherein as we increase the solubility, the number of carbon atoms in our chain, the less and less it becomes soluble. Okay, you can see here a decrease in the solubility of water. Whereas we have here infinity, meaning the solubility is increasing. Then we have also this particular pressure effects covered. So the solubility in particular of gases in liquids was discussed in here. And we know that as pressure increases, solubility increases. So as depicted in this illustration, if we have this gas on top of a particular liquid, if you're going to increase the pressure, your portion of your gases will get dissolved in your liquid. So pressure increases, or as pressure increases, solubility of a gas in a given liquid increases as well. So this is the primary reason that whenever you drink soda and the cap of the bottle of soda, once it is opened, the soda does not taste good as when the soda was first opened. It's because the thing that gives the biting taste to our soda is the dissolved CO2. So once we open the cap, we decrease the pressure, thereby the CO2 dissolved in our soda solution it escapes out of solution. Okay, or gets this solution. It's being taken out rather of the solution. Now we also covered Henry's law in this sense. So this was discussed to you concerning the solubility of a gas as a function of the Henry's law constant and the partial pressure of the gas above the solution. So whenever this partial pressure is increased, the solubility is increased because of this direct proportional relationship between solubility and the partial pressure of the gas. So we covered that. And temperature effects, this is the case wherein as we increase temperature, the solubility of a gas decreases this time. It decreases because your CO2, for example, your CO2 and your O2 dissolve in water. In the case of thermal pollution, escapes from water, thereby subjecting the living organisms in that particular body of water to what we call thermal pollution. It's because the needed dissolved gases in that particular body of water already escapes from it. Thereby, there not being enough CO2 in the case of plants and not enough O2 in the case of animals to support their well-being in that body of water. So that's thermal pollution. So to sum up, as pressure increases, solubility increases in the case of gases. As temperature increases, solubility decreases in the case of gases. So it was also illustrated in here. One exception though is your cesium sulfate. So in this case, class, as we increase the temperature in here, as we increase the temperature, the solubility decreases. Okay, whereas in here, as we increase the temperature, solubility increases. Okay, this is in the case of solids. You see, these are solids. These are not gases. Now, we will continue because these are part only of review. Now, still on temperature effects, and I have already mentioned on thermal pollution. So the one that I have shown to you a while ago, these are for solids. Okay, solids, solubility as a function of temperature. This one, solubility of gases as a function of temperature. So all solubilities decreases as temperature increases. Then we move forward with a different manner of expressing concentration. So we have the mass percentage, we have the ppm, and the ppb. So mass percentage is so easy. You simply place the mass of the component in the numerator and the total mass of the solution in the denominator. That will give you the percentage by mass of that particular component in your solution. Okay. Now, as for parts per million, so from the term per million, instead of multiplying it by 100 in the case of percentage, now we multiply it to 1 million. Still the same formula, mass of component in the solution over total mass of solution. Equivalent set of units for ppm is gram per ml or milligram per liter. Okay. If the value of the concentration is even smaller than the ppm, then we can use the ppb. That's parts per billion. So 1 microgram per kilogram of solution. So 1 microgram of solute per kilogram of solution. And instead of multiplying it to 10 raised to 6, we now multiply it to 10 raised to 9. Still same formula in the numerator, mass of component, and in the denominator, total mass of solution. So this is the three simple way of expressing concentration in terms of masses, and in the case of the ppm, it could be mass per unit volume as well. Okay, now, but in solutions later on in expressing concentration, especially when we do stoichiometric calculations, most often we're using molarity of solution, and also we're using molality. And the most fundamental, the mole fraction. So mole fraction is actually comparable to, so in form, it's quite similar to mass fraction. In here, we just replace the mass to mole. So mole of a particular component over the total moles of the solution. Now with molarity, we change the denominator of moles of component or moles of solute. In here, the numerator is the same as mole fraction of component, but the denominator is now liters of solution. So instead of having mass to mole to mole, in here we have mole to volume, okay, for molarity. Okay? Miss, ang slide, Japon sa factors affecting solubility. Really? How come you did not inform me? Wait, class, ha? This was also the experience of my class this morning. Is it moving now?
Wala pa, miss.
Oh, I'm already moving it. Wait, huh? This is also what my heat and mass transfer me class this morning mentioned to me. Let me check, class, huh? I'll go to ways of expressing concentration. Let me see if you can see it. Factors affecting solubility. Then we go to ways of expressing concentration. Do you see it? Ways of expressing concentration. Okay. Ways of expressing concentration then. So this is what I mentioned regarding mass percentage, parts per million, and parts per billion. Okay. Now we move. And we have here molarity and mole fraction. Okay. The one I last mentioned. Then we have molality. If molarity is capital letter M, molality is small letter m. with the unit moles of solute per kilogram of solvent. So the numerator is similar to that of molarity, but the denominator this time is not volume of solution, but rather mass of the solvent only, not of the solution, but only of the solvent. So it was also illustrated to you last meeting on how to convert from molarity to molality. So just listen to the shared recorded discussion last meeting in your Canvas. It was shared last week. Okay. Now this is just a, shall I say, a graphical representation of how we do computation. So if you're given the volume of the solution and you're provided with density, you can convert the volume of the solution to mass of the solution. Okay? Knowing that density is mass over volume. If you're given the mass of the solute and you want to convert it to moles of solute, you need the molar mass. If you want to determine the molality, the moles of solute to a kilogram of solvent, then that would be needing the mass of the solvent here and the moles of the solute in here. So that would give you molality. If it's molarity, that's moles of solute to volume of solution. Okay? These are the things we ended, I think, last meeting, the manner or different ways of expressing solution concentration. Okay, now for today, as mentioned, we will now discuss the colligative properties of solutions. So when we speak of colligative properties, they depend on the quantity of solute molecules present in our solution. Now, the primary colligative properties that are often encountered when we speak of solution are the freezing point depression and melting point elevation. Now, when you speak of freezing point depression, what does this mean? Will there be an increase in the freezing point or will there be a decrease in the freezing point? When we speak of freezing point depression, will there be an increase in the freezing point or decrease in the freezing point? Okay, somebody wrote in the chat box. Okay, so there is or there should be a decrease in the freezing point of your pure water. For example, if you're going to dissolve solids on it, if water freezes at 0 degrees Celsius, if you're going to dissolve solute on it, any solute on it or solid on it, that particular freezing point is even going to decrease. And as such, it's referred to as the freezing point depression. On the other hand, I think it's already self-explanatory when you speak of melting point elevation. This time, your melting point from the term elevation is going to not decrease, but rather increase. So the melting point of any solid is going to increase or going to be elevated if more solids will be added to it. So melting point elevation. Okay, these are the common colligative properties of solution, but we were going to include there this case of the lowering of the vapor pressure. Okay, so what is this lowering of the vapor pressure? So from the term itself, lowering, a decrease in the what? In the vapor pressure. So non-volatile solvents, when we speak of non-volatile solvents, solvents that are not easily volatilized or does not easily evaporates, reduce. Reduce meaning decreases the ability of the surface solvent molecules to escape the liquid. If there is this reduction in the ability of the surface solvent molecules to escape the liquid surface, then what we have is a case of lowering of vapor pressure. Maglubo ang iyang vapor pressure. Therefore, vapor pressure is lowered. So as mentioned here on the next bullet, the amount of vapor pressure lowering depends on the amount of solute. Now, let's see, for example, here in terms of an illustration, what happens. You have here solvent alone, no solid. no solids present. So this is its vapor pressure, the pressure above the surface of the solvent. What happens if we dissolve a certain amount of solid or solute in this particular pure solvent? There will be a decrease in the vapor pressure, the pressure above this particular solution of solute and solvent. So from here, we could see that when the solute amount increases, the vapor pressure above the solution decreases. As such, it's mentioned here, the lowering of the vapor pressure. If there's no solid, so much the better. You have the pure, we refer to that in higher chem, the pure vapor pressure of this liquid, this solvent. But now, once you have some solute or solid dissolving it already, then we have decreased its vapor pressure. Now, we proceed. So Rayauld's law is the law in which we can apply this concept of vapor pressure lowering. So PA is the vapor pressure of the solute. This is the vapor pressure of the solute. PA naught, we call it PA naught, is the vapor pressure without the solute. In higher chem, we refer to this even when you reach your unit operations. We call to this as the pure vapor pressure of your solvent kung wala siya sang may na-dissolve na solute. And XA is the mole fraction of A, your solute, in the solvent-solute system. Now, this partial pressure, if you look class of A, the partial pressure of A in solution is a function. It's a function of its mole fraction in the solution times its pure vapor pressure, should there be no solid dissolved on it. So then it would be very common sense that when we speak of mole fraction, then this value is less than 1. The original pure vapor pressure, if you multiply to a value less than 1, of course, it will decrease from the original value, which a PA naught, it will be decreased to PA because you multiplied it to a decimal value or to a value less than 1. As such, it's the lowering of the vapor pressure. It's because of this, okay? The mole fraction of the solute present in your solution. Now, recalling what you have learned in the past regarding mole fraction and its relationship to partial pressures and total pressure, using Dalton's law of partial pressure, the partial pressure of a gas component in a mixture of gases is actually its partial pressure, its mole fraction in the solution times the total pressure of your system. Now, this would often be then I think this is written in your chem then as PA over P total is equal to YA. Specifically, when we speak of mole fraction in the gas solution, we do not represent it as XA, but it's okay now since it's just chemistry. But in higher chem, when we speak of mole fraction in the gas phase, that should be YA. And it's actually partial pressure of component A over the total pressure of your system. Kasi in the system, they're already made up of several components. Now, this YA and this XA are equal, by the way. Okay? So if this YA or this XA is less than 1, same here, this PA naught will be decreased to PA because you're multiplying it to a value less than 1. So the mathematical representation of the lowering of the vapor pressure is actually illustrated by Rayauld's law. And it's the same law that you will apply later on in your unit operations under gas absorption. We go back to this very fundamental basic law of the lowering of the vapor pressure. Okay? If you have any question, class, just interrupt me or you may write in the chat box. Now I will continue. No ideal solution. The Rayauld's law that was shown to you is only applicable to ideal solutions, by the way. If Rayauld's law is not anymore applicable since your solution is not behaving ideally, but it's behaving like a real solution, then we have an alternative, and that is your Henry's law. A few minutes ago, I mentioned about Henry's law. I reviewed about what we've discussed it last meeting. So Henry's law speaks of the solubility of a gas as a function of its pure vapor pressure. Okay, now we go to boiling point elevation. So we started with lowering of the vapor pressure for the colligative properties. We have now boiling point elevation. Boiling point elevation, meaning the boiling point of your solution is going to increase due to the presence of solids in it. So in here, the goal is to interpret the phase diagram for a solution. So non-volatile solute, remember this, will always lower the vapor pressure. If the vapor pressure is decreased above the solution, the boiling point of that solution will increase. It will take more time, or it will take an increase in temperature before your solution is going to boil. Why it will take more time, or it will take a higher temperature for your solution to boil? It's because its vapor pressure was lowered. So I'm trying to emphasize here the connection between vapor pressure and boiling point. Lowering the vapor pressure increases the boiling point. Increasing the vapor pressure decreases the boiling point. So they are inversely proportional. So due to the presence of the solute, a few minutes ago, we mentioned that the vapor pressure above the solution is decreased. If it is decreased, the boiling point is going to increase. Now, in here, in the last bullet, there's a mention about the triple point, or the critical point curve is being lowered. Now, I'm not sure if this is already discussed in senior chemistry, senior high school chemistry, but I'm just going to give you an idea what is this triple point thing. But I'm just curious if anybody knows what this triple point is. Of course, without having to Google it, because if you Google it, then you would know. What's your idea about the triple point? Was this ever discussed in your senior high or junior high chemistry? If it's not discussed there, it's okay, class, because it's now being given here, but this is just an intro. It will be discussed further when you go to physical chemistry. It's a 2-phase course. So you have Pchem 1 and Pchem 2, I guess, when come next year and third year. Okay? So the triple point, okay, na-discuss man gali. So nalipatan lang. So the triple point is said to be the point wherein all three states of matter for a particular material coexist. So do kabudlay sa iya yan, no? I-grasp nga at that particular temperature and pressure for a material, all solid, liquid, and gas phases will coexist. But there is that particular point in the phase diagram. So I'm going to show you an example. So this is a phase diagram. This is the original triple point. So this is where the solid, liquid, and gas phases coexist for the particular material in which this one is used to depict the relationship between the behavior of the vapor pressure and temperature for these phases of matter. Meaning for a different material, plus you will have a different phase diagram. So here in the triple point, the solid and liquid and gas phases coexist for this particular material. As a consequence of the colligative properties of solution, whenever solute is present, whenever the amount of solute present in solution increases, there is a, shall I say, a going down. Doga panaog ni siya ang atong triple point, and from this original position, it will now be in here. By the way, we refer to this as phase boundaries. So this is for the solid phase, solid na di siya tanan sa diri nga vapor pressure kag temperature, diri liquid siya, diri gas siya. So now as the case of the colligative properties, if a certain amount of solid is dissolved in your solute, manaog na siya. Ang matabo, kung manaog siya, there is going to be elevation in the boiling point. At 1 atm, your original solution is going to boil here. Original boiling point of the solvent rather. But once there is solute present on it, dissolved on it, it will be increased to this part. Why? Because of the sliding down of this triple point here in the phase diagram. Now, this one is different when we speak of the freezing point. So this is the delta TB, the elevation of the boiling point, elevated in the sense that from this value, it is increased to this. For the freezing point, it's the other way around, class. There is depression. The original freezing point of your solvent, your pure solvent, is this one. However, it will slide to this freezing point here once some solids are present on it already. So I'd like to go back to the previous slide so I can go back to this part here. Therefore, the triple point critical point curve is lowered. Nag-slide down siya. So from this original orientation of the phase boundaries intersecting at this triple point, you have this point now. Nanaog na siya. So there are two colligative properties that you could see in here. The elevation in the boiling point and the depression of the freezing point. The two were mentioned at the introductory part of the colligative properties of solution. And we discuss also the lowering of the vapor pressure, which is, if you're going to ask me, the lowering of the vapor pressure is directly related to the increase in the boiling point or the elevation of the boiling point. As such, class, oftentimes, even in phychem, physical chemistry, when you speak of colligative properties of solutions, these two would suffice already. The elevation of the boiling point and the depression of the freezing point. Okay, so I hope I made you recall the things that you have learned in the past in your chem. Now, how do we account for the elevation in the boiling point? Or we call that the molal boiling point elevation. This is the molal boiling point elevation. So, but this one is the constant. This is a property of your material, and this has a table where you can get this particular constant. So this is a constant. So this particular formula allows you to quantify the increase in the boiling point. So this is the delta TB as a function of the molality of your solution. So ano ganing molality? Molality is mole solute per kilogram solvent, right? So it's a function of your solute in solution and this particular constant. The formula, class, actually for melting point depression is similar to this. We just change this to F and we just change this to F as well. So to illustrate what I mean, amo na siya, class. Okay? So for molal freezing point depression, you have your molal freezing point depression constant, and it's still being multiplied to the molality of your solution. So what happens is ang imo nga freezing point ma-decrease. So kung imo nga boiling point nag-increase, ang imo freezing point ma-decrease if solids, if there are more solids or there are solids dissolved in your solution. Okay? Now, we move on. Any question here? So, if you are asked what are the colligative properties of solution, ang primary thing din na nga pwede nyo masabat would be freezing point depression and boiling point elevation. Although there are other things that you may add to it, but somehow it's related to the first two. So the lowering of the vapor pressure, as I have mentioned, is associated to the boiling point elevation. There's somebody here. Miss Brownout. It's okay, Daniel. Wala kasa. Now, in this table, part na ni siya, class, ng isa ka table that I took from a soft copy of a book. And in here, you have solvents like water, benzene, alcohol, carbon tetrachloride, and chloroform. So these are the normal boiling point of these solvents kung sila lang, kung wala sang solids present. And these are their molar boiling point elevation constant. So you only need the molality. With this, you can get the elevation. So expect an answer which will be higher than this normal boiling point, because these are their boiling points when they are pure. So once there is a solid present, then malubo na siya, ano na siya, ma-increase na siya. Unlike with the normal freezing point class, so this is the freezing point of water. We are very familiar with this. And in the case of benzene, this one. And look at the freezing point of ethanol. Very, very low compared to the others here, which are negative. And you have here the molar freezing point constants of the solvents. So with the molality, you can multiply the molality to this constant here, and you will have the depression, the degree in which the freezing point of pure solvent is going to decrease. Manaog pagid siya. Okay? Because it's depression. There's no worry about the values of this case of B and case of F, because anyway, all you have to do is look it up on tables, or even more so, you can Google it as long as the site that you're using is credible. Another colligative property is osmosis. This is not something that is new. In osmosis, we have this semi-permeable membrane that is used to separate a highly concentrated region from a less concentrated region. It's semi-permeable because it will allow passage of some components of the solution. So in the natural processes in our bodies, we have our cell membranes. And synthetically, we have also cellophane, that is a semi-permeable membrane. So when we speak of osmosis, it is actually the movement, okay, what moves? The solvent, the movement of a solvent from a low solute concentration to a high solute concentration, or from a low concentrated region to a high concentrated region. This movement actually is in both directions across a semi-permeable membrane, but as long as it's always from low concentration to high concentration. As movements move, a solvent rather moves across the membrane, nag-move imo solvent sa membrane, the fluid levels in the arms begin to be uneven. So kung nag-move na ang imo nga solvent from one part of your, say, separated container or tank to another, then expect that there will be also a difference in the fluid levels. What controls, or when will this particular condition stop? So eventually, the pressure difference between the arms stops of osmosis. If there is no more pressure difference between the arms here, then there won't be any movement from the dilute solution to the concentrated solution side. Now, the thing that enables, by the way, the transfer of the solvent from the less concentrated region to the more concentrated region is what we call as the osmotic pressure. Okay? Osmotic pressure represented by pi. So the symbol of the osmotic pressure is pi. And actually, its formula is patterned from the ideal gas law. See this? P, V, and RT. So the pi here is the pressure. So the osmotic pressure of a solution actually is a function of its, you have here, moles over volume, molarity. Okay, moles over volume is molarity times the universal gas constant times the temperature, the absolute temperature. So this pressure, this osmotic pressure is the one that will stop the osmosis. So is the pressure required to stop the osmosis? I think the osmosis will stop when both levels in here, as you could see, both levels of the liquid in here already are at the same level, or the pressure from one level is the same as the other. So there won't be any movement anymore. Now, if the two solutions that we're talking about has the same osmotic pressure or the same pi, they are referred to as the isotonic solutions. So another added vocabulary, chemistry vocabulary to yours. So isotonic solutions, when two solutions with the same pi separated by a semi-permeable membrane. Okay? Now, I will continue. So this is the last part of the slide already, class. So if we're done, we will have a break and we will have some exercises to check whether you know how to apply what is discussed. Then I'll leave the remaining time to you to process your activities. Now, colloids. Colloids is associated to the what we call the Tyndall effect. So colloids are actually suspensions, particles that remain suspended indefinitely, meaning hindi gina siya class mag-settle. So suspensions are in which we have suspended particles that are too small to drop out of the solution by virtue of gravity. Normally, the particle size in your colloidal mixture ranges from 10 to 2,000 angstrom. So very small. Now, the Tyndall effect can only be, this phenomenon can only be experienced when you have a colloidal suspension. Wala ni siya sa solution. This only happens in a colloidal suspension. So colloid, so this, we're not talking about solutions anymore, but rather we have a special type of solute and solvent wherein the solute remains suspended indefinitely in the solvent, and we are now talking about colloids. So this is the ability of this particular shall I say solute and solvent mixture to scatter light. So the beam of light can be seen through the colloid solutions. In solutions, we don't see this one. Okay. Now, and here are the different phases of a colloid. So, common na sa aton nga colloid liquid. Kiti amo na ang experiment nga gina-perform sa high school. So, you have here, the first column is the phase of your colloid. Then, in the second column, you have here the dispersing substance. The dispersing substance in our language, dira nagalutaw-lutaw ang mga solids. The dispersed substance, amo na sila ang remains suspended indefinitely. Okay, and you have here that type of the colloid. We mean is the name associated with such a colloid and an example. So you can have a gas dispersing solvent to a solute that is gas, but there's no particular colloidal type on it. So meaning, we don't have such a thing as a gas remaining suspended indefinitely and another gas. Because primarily, when we speak of a gas to a gas, we have a solution. So none, because all are solutions. Okay, we only have, in the case of the others here, you have a gas, your dispersing medium is a gas, and your substance that is dispersed or remains suspended is your liquid. And this is a type of colloidal mixture, which is an aerosol. So an example is your fog. The fog. Diba sa bababukid, you have this gas thing that you see. But whenever you are in that particular region where there is fog, you will see that, let's say, you'll get easily, ano siya, let's say this man, basa kay tungod nga, ang iya nga liquid is, ang iya nga solute is liquid. So the example is fog. Okay? Early morning na ni siya gani. Di kung adlaw na, wala na siya in some areas. Now, we can have a gas, the dispersing substance is a gas, and your solute that remains suspended is solid. So this is also called aerosol. Just like the first one is aerosol, but the example of this is smoke. Or shall I say, inabla mga smoke, especially sa chimney, that has particles on it remaining suspended. So those are smoke. Now, the other examples are in here. So your liquid, your gas to liquid is foam. An example is whipped cream. Unique because this time your solute is the gas, your dispersing medium is liquid. So you have a foam. In the case of liquid to liquid, you have emulsion, and that's the case of milk. In the case of solid to liquid, we have the sol, and paint is an example. So paint is a colloid. And we have a gas in a solid. Imagine a gas particles remaining suspended in a solid, and that's the case of the solid foam. An example of which is your marshmallow. Diba? Pagkagat mo sa marshmallow, wala na, natunaw na siya. Ang imo gas solutes remain suspended in that case in your solid. Then we have liquid in solid, the solid emulsion, which is the butter. Liquid to solid, to butter. And then solid to solid, so we call this the solid sol. And I think this is the only example that they can give to this, the ruby, the glass ruby, or the ruby glass. So these are colloids. They are not solutions because otherwise, if your solute will not remain suspended, you have a solution. So opposite ni sila sang colloids kag sang solutions. Now, there is this why we call hydrophilic and hydrophobic colloids. So phobic, phobia, philic, philia. So muna siya. So when we speak of water-loving colloids, hydrophilic. Philia daw love, philic. Water-hating colloids, hydrophobic, phobia, fear. So, and this actually, this property of colloids to be water-loving or water-hating is the one that is being used by detergents and soaps to get the dirt in our clothes or to get the dirt on anything that they are used to clean up. So when you speak of this hydrophilic and hydrophobic characteristic of our colloids, we focus on water because the hydro, meaning water. So molecules arranged in here themselves so that hydrophobic portions are oriented towards each other. The same thing with hydrophilic portions. So most dirt stains on people and clothing are oil-based. So oil-based sila. Soaps are molecules with long, take note, hydrophobic tails and hydrophilic heads that removes the dirt because they are hydrophilic by stabilizing the colloid in water. Now, in the case of its application in our stomach, so bile excretes substances like sodium stearate that forms an emulsion with fats in our small intestine, enabling us to poop the excess fat that we eat in our diet. That is why class na ginasuggest nila for people that are, yung term nila lang hypertensive, dali ma-high blood, mayo pa makaon ka baboy kay dasig sa i-digest ang poop mo ya, madalala na ya ang fat sa excess fat sa imo poop unless otherwise wala ka gagiho-giho nga even you don't have regular bowel movement. Now, pero kung gakaon kaya beef budlay na sa i-digest kay ang fat sa beef, kung kihado ng karne, makita nyo ang fats ara sa tunga-tunga, sa tissue, budlay na siya class i-digest. So these are the fats that remain in our bodies. The fats nga ginastore gid sa tissue, di kung mag-sobra-sobra na ginaklag na nilang ang arteries ng aton heart. Kaya mo na nga ka-stroke ang iba ng mga tao. So mas mayo pa nga kaong ka baboy, perme, sa kaong ka karne, perme, kaya ang karne very dangerous din. So, emulsifying agents help form an emulsion. So, this is one thing that is being used when emulsions are needed for a particular application. How do we remove colloidal particles? So, colloidal particles are too small to be separated by physical means. You mean, i-filter ko lang ni Miss hindi na siya pila pa na kadako sang numbers ang Wattman filter mo, hindi na siya kay remain siya suspended. So colloid particles are first coagulated. So there is this use of a coagulant. It's an added substance in, let's say, in a colloidal mixture that helps the suspended particles to aggregate or magkumpol-kumpol bla sila class, agglomerate, they form one big chunk. That way, they can easily be removed by filtration. If not, ma-remove man siya by filtration siguro, pero kinahanglan mo nga watman, guro nga filter, taas-taas na sang number. Inang ang iya nga ano, ang iya nga shall we say, opening sa pores ng imo nga watman filter is too small. But with that would really take time. Okay? So the different ways of coagulating suspended particles are enumerated here. So we can have them heated or we can add something. As I have mentioned, you can add an electrolyte, which neutralizes the surface charges in your colloidal particles. If the surface charges in your colloidal particles are neutralized, this allows the suspended particles to agglomerate with one another or aggregate, mag-chunks sila, they form chunks. Heating can also help remove colloidal particles. So it's also a method for coagulation. So in here, it's explained that colloid particles move and are attracted to each other when they collide. So heating increases the state of excitement of the molecules. If they're too excited, they get to collide. The probability of collision is higher. So when they get to collide to each other, attraction is induced or enhanced. So kung attracted na sila, di madako na sila, hapos na sila i-remove. So colloids or colloidal particles are first coagulated before they are filtered or removed. By means of, it could be sedimentation, kung dagko na gid ang naimo form nga aggregate, then by sedimentation, they can settle down already. But once they are very small, they cannot, or it would be very hard for them to settle down. Okay, so this ends the chapter on solutions. I'll finish everything in an hour. Any questions so far? I'll give you a 10-minute break. Then I'll give you some exercises to process. I'll guide you as well. Probably we can have in an hour or less. If we can cover everything, then the rest of the time will be for you to use. To do your, I gave you an activity that is still due December 9, and we'll add more to that under this particular module. Okay, any question here before I give you a break on what we have discussed? Here. Okay, wala. Sige come back at 1:36. That's 10 minutes after. We will continue with this class, okay? I'm just here. Just don't log out of Zoom. Just remain there and then come back after 10 minutes. That would be 1:36. Okay, I'll stop sharing now. Now, let me share to you the set of exercises that we will process. So it will cover the first part of the computations, which I reviewed everybody a while ago. So the exercises that I've selected here does not simply ask you to determine normality, molality, and something like that. But out of the concepts that we have discussed, we will determine the required information. Okay, so we will process number 1. Okay, number 1. What mass of solute is needed to prepare 1 liter of a 0.125 molar potassium sulfate solution? So we're asked for the mass given the volume of the solution and its molarity. So allow me to go to our Jamboard and we'll start writing our solution. Okay, so we have it here. Now, so in terms of the given, can you see the Jamboard class?
Yes, Miss.
Okay. So we're given a volume, which is 1 liter, and a molarity, which is, I'll just go back to the problem, 0.125 molar. So this is 0.125 molar of potassium sulfate. So you are required to determine the mass. So the mass of the solute in this case. So this is the unknown. So can you tell me what do we do first in here? To get the mass, what do we do? Okay, get the moles first. Okay, I want the others also to interact with me. I don't want only 2 or 3 usual names I see on the chat box. So this is very true. Very good, John. So you're going to determine the number of moles first. So we know that molarity is equal to the number of moles over the volume of the solution. So you substitute here molarity point. Where did I get the 6? So you substitute the value that is given, which is 125, and we will determine the number of moles, and the volume here is 1 liter. So this follows then that your number of moles is simply 1.125 moles. Now, how do I get the mass? How do I get the mass? I already have the number of moles. How do I get the mass? Molar mass, correct? Kyle, I will use the molar mass. How am I going to use the molar mass in this case, Kyle? So your number of moles is 0.125 potassium sulfate, and I want the mass. So I will have 0.125. I'll do what? I'll do what? I need the mass. So what I do is I have already illustrated this particular technique to you. That's dimensional analysis. E-convert. Pwede man. You convert or you use dimensional analysis. So in this case, you have here moles, K2SO4, and as suggested by Kyle, we use the molar mass. So we will multiply. So what's the molar mass of potassium sulfate? So I will place here per mole of potassium sulfate. And I don't recall the atomic weight of potassium, but I know sulfur is 32. 16 times 4 is 64. So I need the atomic weight of potassium. So 174.26. So this is it, 174.26 grams of potassium sulfate. So this is what I meant with dimensional analysis. You manipulate your units that way, the unit that you are needing will be the one that will be left. So we can eliminate moles of potassium sulfate by multiplying the number of moles by the molar mass. So our answer here is equal to, let me see if somebody gave me the answer already, 21.78. So 21.78 grams potassium sulfate. See, it's very easy. You use the formula for molarity to get the mass of the solid that is to be dissolved in 1 liter of solution. Okay, so thank you for the answers that were provided. So this is for our number 1 based on the given here. So I will share back our set of problems. Number 2, calculate the molarity of a 12.4 gram KCl of potassium chloride in 289.2 ml of solution. So this time, this is more straightforward and this is more like it wherein you will have substitution to the formula. Only that there's a need for you to convert. So you'll be needing here the molar mass of KCl. Okay, so I'll go to our Jamboard. And we'll go to our number 2. So you're given mass. So the mass of Ki is given to be 12.84 grams of potassium chloride. And then 12.4. And then the volume is 289.2. 12.4 only, class. And we have a volume of 289.2 ml. So you are required for the molarity. Okay, so we start with the formula because it's asking already for molarity. So molarity is equal to the number of moles divided by the volume of the solution. Now, in order for us to get the number of moles, you get the molar mass of, you need the molar mass of potassium chloride. Okay, so we need the number of the molar mass or the molecular weight of potassium chloride. Can you give me the molecular weight of potassium chloride? 74.55. So 74.55. Okay? We need to determine the moles, so we need to divide the mass by the molar mass. So number of moles is the mass over the molar mass or the molecular weight. It's 12.4 grams in here. We divide it by this. 74.55 grams per mole. So you cancel the gram unit and the mole unit goes up. So the answer for our number of moles is 0.166 or 0.17. Thank you for the answers, 166 or 0.17 moles. Okay, then we go to our formula. So M is equal to, now you have the number of moles or 0.166. We divide it, so this is moles. We divide it by the volume. The volume that is given to us, class, is in ml. 289.2 ml. What do I do with this? What do we do with the ml? We will convert to liters because molarity is moles per liter. So conversion, 1,000 ml in 1 liter. So we cancel the ml unit. So we have now a molarity of, what's the answer for our molarity? 0.57. Okay, so 0.57. Molar. You get it? So do you follow? Okay, so 0.57. We go to number 3. Now go back to our problem set. Number 3. Number 3 asks you to calculate the molality. Molality, moles of solute per kilogram of solvent. Given that you have 2.89 grams of sodium chloride dissolved in 0.189 liter of water. Now, density of water we know is 1 gram per ml. Okay, so what do we do? So we have the mass of sodium chloride, which is 2.89. So let's go to our Jamboard. The mass is 2.89 grams of sodium chloride. And then it's stated there, as read to you, that this will dissolve. It will be dissolved in 0.159 liter of water. So the volume is 0.159 liters of H2O. Okay. We are required to determine the molality. And what is molality? Molality is moles solute per kilogram solvent. So if we need the moles of solute, if we can go directly to the solution, because it was already illustrated in the previous example, how to get the moles given the mass. So we have 2.89. I'll place here 2.89 grams NaCl. I need the molar mass of NaCl. Can you please provide me with the molar mass of NaCl? That is 58.44. So 58, I'll place it here, 0.44 grams to every mole NaCl. So I'll cancel this one. Now my numerator has a unit of mole NaCl. Now what about the denominator? It says here that you are to use 0.159 liters of water. So I'll start with it. 0.159 liters of water. Water being the solvent. And the problem gave us the density of water, which is 1 gram per ml. That 1 gram per ml, class, could be converted to, sige, I'll place here 1 gram per ml. It can be converted to kilograms because we want kilograms, not grams. But before that, the liter here and the ml don't agree. So convert the 1,000, rather the ml to liter. Okay, so now I convert the liter. Next, convert the grams to kilograms. So I'll place here 1,000 grams to 1 kilogram. So now you will just cancel the 1,000 and you will just cancel the grams here and the grams here. The ml here and the ml here. Leaving you with the unit and the denominator, which is kilogram. Now, the molality then was solved straightforward. Not we have to pass first to the N, then convert the volume to kilograms of solvent, but we directly place it in here in our numerator and the denominator. I'm referring to the necessary conversion. Okay, let's see. What's the molality? Okay, Pearl gave me 0.31. 0.31 mole NaCl. Okay. Okay, Dana also gave me the same thing. NaCl per kilogram water. So notice the units that appear in our molarity. Moles of solute per kilogram of solvent. Okay, so 0.31 mole per kilogram solvent. Okay, any questions so far? Okay, if there's none, we proceed with the last two. Go back to our problem set. Calculate the mole fractions of each element. So how many elements we have in sulfuric acid? 1, 2, 3. In 19.4 grams of sulfuric acid in 0.251 liters of water. So calculate the mole fractions. Okay, so you have, okay, in this case, class, since we dissolve our sulfuric acid in water, we will determine the mole fraction of sulfuric acid as a whole and water as a whole in the sulfuric acid water solution. You get me? So calculate the mole fraction of, so I will edit this one. Of each in 19.4 grams of sulfuric acid in 0.251 liters of water. So that way you will know that you will get the mole fraction of sulfuric acid and the mole fraction of water. So this will be requiring two answers in this particular number. Okay, so we go back again to our board. And we go to, this is our fourth example already. We are given 19.4 grams sulfuric acid. So mass of sulfuric acid, 19.4 grams. Next, so we have mass of sulfuric acid and 0.251 liters of water. So volume of water is 0.251 liters. You are required to determine mole fraction of each component in the solution. Okay, so your solution has two components, sulfuric acid and water. So this is an aqueous solution. So solution. Next, we go to solution. The first thing you do is determine, what do we need to do first? I will ask, what will you do? You will determine the, what will you determine first? Sige, so there's a suggestion, determine the molecular mass or determine the molar mass of each. Okay, you will use it anyhow. Sige, so we will determine the molar mass of each. So molecular weight, sulfuric acid, molecular weight of H2O. This I can readily answer. What about sulfuric acid? We have 98. So we have 98. I will not anymore write the units. Now I have this, then what's the next thing you do? You determine the what? Remember, you're after the mole fraction. Determine the number of moles of each component. So determine the number of moles, correct. Determine the number of moles. So I will determine N of sulfuric acid That would be the given mass in here, 19.4 grams. I will convert to moles by dividing by 98 grams for every mole. That will give me an answer which is 0.198. 0.198. Thank you. So this is now moles of uric acid. Then I'll go to moles of water. How do I find the moles of water? Your water is given in volume. So you have 0.251 liter. But a while ago, what did we learn? Density of water can be here. 1 kilogram per liter. So then I'll place here kilogram, 1 kilogram per liter. So now I have converted liter to kilogram. Then I will use the conversion 1 kilogram, 1,000 grams. So I cancel the kilogram. Now my grams can be converted to moles. So this is grams. So I'll place here 18 grams for every mole H2O. You get it? So you have 251 divided by 18. What's our answer? Sila lang po nag-help diyo. Ang nag-participate, 13.93. 13.93 moles. Okay? Next step, what would you do? You have the moles of each component. What do? You get the total number of moles. That way, you can easily get the fraction. So 0.198 plus 13.93. That's the answer. 14.128. Okay. Then mole fraction. So X, right? Mole fraction is X. X, H2O, and X. What's the other substance? Sulfuric acid. Sulfuric acid. So for H2O, we have 13.93 divided by 14.128. For H2O, I wrote H2O for both. So this is sulfuric acid. H2SO4. So for our SO4, sulfuric acid, we have 0.198. So 0.198 divided by 14.128. So you can give us the answer here. So this will be 99. This would be 1%. Because the sum should be 100, right? So this is 0.99 and this is 0.01. The sum of the two mole fractions should be equal to 1. So 0.01. You get it? So we have solved problems now starting from mole fraction down to molarity and molality. Any questions so far before we go to the last? Any question? Okay, there's none. So this is it. So the last. I'll share it here. Okay. Calculate the mole fraction, molarity, and molality of ammonia if it is in a solution composed of 30.6 grams ammonia in 81.3 grams of water. The density of the solution is 0.982 gram per ml and the density of water is 1 gram per ml. Okay, you're given the density of water, you're given the density of the solution. Okay, so what do we do? Here after mole fraction, the same thing. Determine the moles of ammonia and the moles of water to get the mole fraction. To get molarity, you already have the moles of ammonia. You just divide it by the volume of the solution. How will you get the volume of the solution? You are given here the density of the solution. How will you get the volume? Anybody? You get the, yes, volume density is mass over the mass over density. Yeah, mass over density is equal to the volume. That's very good. Okay, so get. We will solve. Okay, this is our last problem. Let me share to you our Jamboard again. Given. We have the mass of ammonia. Okay, we'll get it from our problem set. The mass of ammonia is 30.6. Okay, 30.6 grams. Next, that is given. You have the mass of water, 81.3. So mass of water, 81.3 grams. Then, in the last statement, it says density of the solution is 0.982. Okay, so density of solution is 0.982. So gram per ml or kilogram per liter. Density of water is 1 gram per ml. Now, what are you required? Mole fraction, molarity, and molality. Okay, so we want the moles. So we start with the number of moles. Number of moles of ammonia. Number of moles of water. So your ammonia is 30.6. So 30.6 grams. Thank you for the molar mass. Beatrice, so you're 17 gram per mole for ammonia. You will have now the moles of ammonia. For water, the mass of water is 81.3. So 81.3 grams. I'll have here 18 grams and I have 1 mole. So I cancel this one. So I'll have now the moles of each. Okay lang. Okay lang. Nag-run out. Sige lang. So the 1.8 is for the ammonia. And this one is for the water. So the total number of moles is the sum of these two. So you will have 6 point, this is 5 plus 3, 2, right? Then you can determine now the x. So x of ammonia, that would be 1.8 divided by 6.32. And you will have here, place here the X of water. You have 4.52 divided by 6.32. Again, the sum of the two should be equal to 100. Okay, what's the mol? 0.28 in here. And for water, we have 0.76. Okay, so see, they will all be summing up to 1. Now, we're done with the mole fraction. Okay, mole fraction. We go to molarity. 0.72. It's okay. 0.72. It should be 0.72 because it will go beyond 1. 0.72. Okay. Thank you, Kesel. So now we go to molarity. Molarity. Mole solute per volume of solution. Okay? Now, our moles of solute here is the moles of ammonia. We have it here as 1.8. So I'll place here 1.8. What about the volume of the solution? You're given the density of the solution. So the volume of the solution is the mass of the solution over the density of the solution. So the first thing that we're going to do, class, is determine the total mass of the solution. Total mass of the solution. The total mass of the solution is the mass of this ammonia and water, right? Ammonia and water, if you take the sum of that, that would be the mass of the solution. And the answer is 111.9, right? Total mass, 30.6 and 81.3. So this is 111.9, correct? 111.9. Now, I have already the total mass. I need the volume of the solution. So that would be the mass of the solution, grams, divided by its density. So the density of the solution is given to be 0.982. So I have 0.982 gram per ml. So I will have now the volume in ml, which is 113.95. But this is in ml. I want it in liters because here this is volume in liters. So I will divide by 1,000 to give me the liter unit in my volume. So my volume is 0.114, right? Correct. Then I go back here. So this is moles ammonia over 0.114 liter solution. Okay? Giving us a molarity of 15.79. Okay. So see? Now last, molality. The small m. So masunod na lang na siya sa pang determine ta kaina. Moles solute per kilogram solvent. In this case, that's your water. So moles of solute, we have it here at the beginning, 1.8. And your kilogram of water, of solvent, which is water, where will you get it? You are given the mass of water. So, pariho man kaina. Volume of water is equal to its mass, which is 81.3 grams divided by 1 gram per ml. The density of water. This will give us an answer in ml, right? By the way, it's kilogram solvent, so there's no need for us to determine the volume. Si Miss Ali na ara sa ulo niya, molarity gyapon. So if it's kilogram solvent, it's just pure conversion. Okay? So we'll have here 81.3 grams. We divide it by 1,000. Okay? This is kilogram water per mole of solute. Let me just go back if it's 81.3. Okay. So we have a molality of, molality is 22.14 mole ammonia of, so this is mole ammonia per kilogram water. Your molarity here will have a unit. Okay, I place the capital letter M. So you know your way already on this manner of expressing concentration of solutions.